In 1989, the Japanese company Sony released the world's first commercial player with rechargeable batteries. Journalists described it as revolutionary. Wireless music and no need to change batteries every few hours. Inside were nickel-cadmium batteries. A few years later, those same batteries found their way into portable video cameras, the first cordless phones, and professional power tools. Production took off. Hundreds of millions of batteries went into the consumer market worldwide, and then into trash bins. Because no one really thought about what would happen next. The metal inside these batteries is cadmium, and the story of the batteries is one of the simplest stories about it. But what happens next gets more complicated. Welcome to the Fool's Gold channel. Today we're looking at element number 48. You know, I've spent quite a bit of time with cadmium. Not literally, of course. I've read studies, looked at court documents, understood nuclear physics and solar panel patents. To be honest, I was expecting a rather interesting element, but I didn't expect one so densely packed with stories. A single metal that is simultaneously at the heart of the first nuclear reactor, the 2023 Nobel Prize in Chemistry, the Japanese environmental disaster of the 1950s, your bread, right now, and in the international standard of length that lasted 33 years. Let's start as usual with the story of its discovery, because it's absurd in the best sense of the word. 1817, the Kingdom of Hanover. A young chemist, Friedrich Strohmeyer, or in the German version, Strohmeyer Bordula, works as a pharmacy inspector. His job is to visit pharmacies, take drug samples, check quality, and issue fines to violators. A typical bureaucratic routine that in no way suggests a scientific discovery. In one pharmacy, he takes a sample of zinc carbonate, a common substance then used in medicine as a mild astringent. The standard test is to heat it up and observe the color. When heated, zinc carbonate decomposes to zinc oxide and should yield a white powder. This is chemistry. This is the rule. This is obvious to anyone who works with zinc compounds. The sample turns yellow. Strohmeyer could have decided that the sample was contaminated with something foreign, fined the pharmacist for poor quality goods, and moved on. Instead, he took the sample back to his lab. Several weeks of chemical operations, dissolution in acid, precipitation, filtration, calcination, repeated purification. Layer after layer, he removed known components. In the end, at the bottom of the crucible, there was a tiny amount of an unfamiliar metal. Silvery white, soft, very similar to zinc, but not zinc. The density was different. The melting point was different. The chemical reactions were different. He named the metal cadmium, from the Greek cadmium, the ancient name for zinc ore. The name is precise, almost literal. Cadmium lives within zinc minerals, hiding in their crystal lattice, and never forms large independent deposits. This is an unflattering metaphor. It's the literal geochemistry of this element, and I'll definitely explain this mechanism a little later. An interesting detail, almost simultaneously in 1817, two other German chemists, Hermann and Rollo, independently discovered the same element in Satatun in Salina mines. Strohmeyer's priority is secured by right of first publication, but the fact that three independent discoveries occurred in 1 year is no coincidence. By that time, chemical analysis methods had reached the necessary sensitivity. Analytical chemistry in the first half of the 10th century was developing rapidly. Gravitational methods, precipitation, reactions, and spectral analysis would appear a little later. Cadmium was always there. It's just that no one looked closely enough before, and the instruments weren't sufficient. Now, the origin. Where does cadmium come from on Earth anyway? Those who have been watching the channel for a long time know this point by heart, and I understand. But every episode is found by people discovering the Fool's Gold channel for the first time, and it would be unfair to leave them without context. So I'll keep it brief and only talk about cadmium specifically. And if you want a more expanded version about neutron stars, our process, and how heavy elements are born, it's all in the progeny episode. So, cadmium, with its owl of protons, is an element that a normal star can't synthesize. The sun stops at approximately iron. Further, thermonuclear fusion requires more energy than it releases. Cadmium requires a catastrophe, a collision of neutron stars or the collapse of a massive star into a supernova. In a split second, with a monstrous neutron flux density, nuclei capture neutrons faster than they can decay, and heavy elements, including uranium, are formed. Every cadmium atom on Earth has gone through this path. The catastrophe is somewhere in space. The dispersion of matter, the gas-fueled cloud, from which the solar system formed 4.5 billion years ago. Okay, billions of years in minerals. And then a streamer with a routine check of pharmaceutical powder. The cadmium content in the Earth's crust is about 0.1 to 0.2 milligrams per kilogram of rock. Not much. For comparison, the copper content in the Earth's crust is about 50 milligrams per kilogram, more than 200 times greater. But the main feature of cadmium is not its absolute quantity, but its behavior. The atomic radius of the cadmium ion is 95 picometers. The atomic radius of the zinc ion is 74 picometers. Close enough for what geochemists call isomorphic substitution. One ion takes the place of another in the mineral's crystal lattice without disrupting it. Cadmium is incorporated into the crystal lattices of zinc minerals, such as fluorite, midsonite, and columine, and sits there unnoticed. That's why Strohmeyer found it in a zinc compound. It's no coincidence, but a geochemical regularity. Cadmium has its own mineral greenockite, a yellow cadmium sulfite, CDS. It's collectible and beautiful. It's named after Lord Greenock, on whose Scottish lands the first samples were found in 1841. It has almost no industrial significance. There are no large, independent greenockite deposits anywhere in the world. Therefore, all industrial cadmium, approximately 25,000 tons per year, is obtained globally as a byproduct of zinc ore processing. Zinc smelters smelt zinc. Cadmium ends up in dust from gas cleaning systems, in slag, and in washing solutions from electrolytic refining. It is captured, purified, and sold separately. The world market price ranges from $1 to $3 per kilogram. Frankly, I think this is astonishingly low for a metal used in nuclear reactors, solar panels, medical diagnostics, and quantum technologies. The reason is simple. Incidentally, it's a bit paradoxical. Cadmium is produced regardless of whether it's needed at the moment. A zinc smelter can't stop cadmium production without stopping zinc production. Supply is insensitive to demand for cadmium, hence the chronically low price. I even feel a little sorry for it, considering its role in human life. The largest producer is China, with about 8,000 tons per year. That's about a third of the world's total. Then there's South Korea, Japan, Kazakhstan, and Canada. The geopolitics of cadmium are inseparable from the geopolitics of zinc. This is important to understand in the context of our discussion of solar energy, which will come a little later. Now let's shift gears slightly from dry statistics and turn to artists, oddly enough. Cadmium yellow appeared on the market around 1850. Before this, artists worked with yellow pigments, each of which had a serious flaw. Lead tin yellow was stable, but it produced a dirty, muted tone, not at all what was needed for rich southern landscapes. Chrome yellow faded in the light faster than desired. Baka. Incidentally, I discussed this paint in detail in the issue about chrome. I'm not implying anything. Indian yellow was organic in origin and also lost its saturation. Cadmium sulfite seemed like a solution. Bright, saturated, resistant to light and heat, and compatible with oil binders. Artists loved it. Later, cadmium sulfite selenide, where some of the sulfur is replaced by selenium, was used to make cadmium orange and cadmium red. The more selenium in the ratio to sulfur, the redder the pigment. This gave artists a whole range of warm colors with equally high light fastness. Claude Monet, in his late period, especially in his Water Lily series, worked extensively with cadmium paints. Renoir did the same. Van Gogh, the Yellow House, Sunflowers, and The Night Cafe at Varley used cadmium pigments in key works. And here's where history takes an unexpected turn. Belgian chemist Corinne Janssens of the University of Antwerp studied the condition of old master paintings. He literally examined the paintings at the molecular level without touching them and discovered something alarming. The paintings are stored in a perfectly controlled museum environment. A stable temperature of 18 to 20 degrees Celsius, relative humidity 45%. Limited lighting with UV filtration. It would seem to offer complete protection, but the cadmium yellow pigment oxidizes and degrades under the influence of light, oxygen, and traces of chlorine in the air. Even in the controlled atmosphere of a museum, these factors are present and slowly transform into colorless degradation products. The reaction is slow, and changes over the course of a year are imperceptible to the naked eye, but it occurs continuously. This is why Janss's group, in parallel with their degradation studies, developed non-destructive monitoring methods. X-ray fluorescence analysis is performed directly through the canvas surface, without taking a sample or exposing the painting to view. The results were published in specialized analytical journals. This allows the pigments to be checked every few years and changes to be recorded before they become visibly visible. Curators of major collections at the Van Gogh Museum in Amsterdam and the Metropolitan Museum in New York have begun to implement these methods into their routine practice. Cadmium paints are still sold in professional lines. Alternatives are still inadequate in applications requiring extreme heat resistance, such as industrial marking of high-temperature parts, coating of aircraft components, and industrial furnace components. Manufacturers are required to include toxicity warnings. Artists work with precautions. So, we move from the artist to the first nuclear reactor, the encrypted phone call that announced its launch, a Japanese river, and the most unexpected moment of release from where exactly cadmium is entering your body right now. On December 22nd, 1942, Arthur Compton called James Conant, head of the National Defense Research Committee. The conversation was over an open phone line. No direct text, everything in code, wet-showed. An Italian navigator has just landed in the New World, said Compton. Conant asked, how are the natives? Compton replied, very friendly. The Italian navigator was Enrico Fermi. The New World was a controlled nuclear chain reaction, the first in human history. It occurred in the basement beneath the stands of Stuckfield Stadium in Chicago and was immediately classified. The war was on. Anything related to nuclear physics was state-run. The farmer led a team of about 10 scientists and engineers who built a reactor from graphite blocks and uranium bricks. The design was called Chicago Pile 1. It looked exactly like its name. A stack of blocks hand-stacked under the stadium's bleachers. There was no containment vessel, no emergency cooling system in the modern sense. The reaction was controlled by cadmium-coated rods. The cadmium stopped the reaction when the rods were inserted into the core. The cadmium allowed it to continue when they were withdrawn. The operator on duty held a rope that could, with a single movement, return the cadmium rod to its original position. Without this control, the first nuclear reactor could neither be safely started nor shut down. If you're wondering why cadmium and not something else, your question is correct. And the answer is concrete. The nucleus of the isotope cadmium-113 has a thermal neutron capture cross-section of approximately 20,000 barns. Let me explain what this means. A barn is a unit of area in nuclear physics. One barn is equal to 10 to the negative 24th power of a square stimeter. This is an extremely small area, but it is a standard unit in nuclear physics. The neutron capture cross-section is not the literal area of the nucleus, but the probability of interaction expressed in terms of the effective area. The larger the cross-section, the higher the probability that a passing neutron will be captured by the nucleus. For most elements, the thermal neutron captured cross-section is in the single or tens of barns. For cadmium-113, it is approximately 20,000. This means that a neutron flying toward the cadmium nucleus has a very high probability of striking it and being absorbed before it can cause uranium fission. Cadmium literally eats neutrons. You insert a cadmium rod into the core, the neutrons are absorbed, the chain reaction slows and is quenched. You pull it out, the neutrons fly free, the reaction accelerates. You pull out a little more, the reaction is a little more intense. This is the principle of nuclear reactor control used throughout the world to this day. Since 1942, there have been no fundamental changes. Materials, designs, and safety systems change. The principle is the same. Since we're talking about the nuclear physics of cadmium, there's one more detail I can't ignore. It personally surprised me during the preparation. Cadmium has 8 naturally occurring isotopes, but only 6 of them are strictly stable. This is one of the highest values in the periodic table. Only tin has more, with 10 stable isotopes. This is because cadmium's atomic number is close to the so-called magic numbers of nuclear physics. The magic numbers of protons and neutrons, 2, 8, 20, 20, 28, 50, 82, and 126, correspond to filled nuclear shells determine to how filled electron shells determine the special stability of noble gases. Cadmium's proton count is 48, close to the magic number of 50. This explains the unusually high number of stable isotopes. Now a detail that sounds like an error, but it isn't. Cadmium-113 is technically unstable. It is a beta emitter, but its half-life is about 8 quadrillion years. A quadrillion is a 1 followed by 5 zeros. Quadrillion is approximately 580,000 times the age of the universe, which is currently about 13.8 billion years old. For any practical purpose, including a nuclear reactor, this isotope is completely stable, and it holds the record for neutron capture. Now to what happened in Japan. I want to tell this story a little differently than usual because there's a point that's almost always overlooked. The Jinsu River flows from the mountains of Toyama Prefecture to the Sea of Japan. It's about 120 kilometers long. The valley is fertile. The Preselvo region has a centuries-old history. Upstream in the Haida Mountains is the Kamioka zinc mine owned by the Mitsui Kazan Company. By the 20th century, it was a major industrial enterprise. Wastewater containing cadmium, zinc, and lead flowed into the river. This was absolutely standard practice at the time. Not a Japanese peculiarity, but the norm everywhere. Industrial waste was discharged into rivers all over the world. The concept of maximum permissible concentrations of heavy metals in water simply didn't exist. No one measured them. No one required them to be measured. Farmers along the Jinsu irrigated their rice fields with the river's water. Cadmium leached into the soil, was absorbed by rice from the soil, and ended up in the grain. People ate rice daily. Most rural residents had little other food choice. The post-war diet was poor. Cadmium accumulated in the body year after year, decade after decade. The first complaints of severe bone and joint pain and skeletal deformities were recorded in the 1910s. The disease was called itai. A direct translation from Japanese means pain. This is what patients cried out at the slightest movement. Bones became so brittle that they broke when coughing. Dozens of fractures were recorded in some patients during the course of the disease. A local doctor, Naru Hagen, began systematic observations in the late 1940s. He mapped cases of the disease and saw a clear geographic pattern. The sick were concentrated in areas irrigated from the river downstream of the mine. He hypothesized contamination. Mitsui Kazan hired its own experts. They concluded there is no connection. Lawsuits were blocked. Researchers who published inconvenient data were pressured. Alternative explanations were put forward. Nutritional deficiencies during and after the war, heavy physical labor, local climate, hereditary factors. Each of these explanations sounded plausible on its own. Collectively, they created enough confusion to drag out the process for years. In 1961, Japanese researchers published a paper establishing a direct link through a specific biochemical mechanism. Cadmium accumulates in the cells of the proximal tubules of the kidney. This is the section responsible for reabsorbing nutrients from primary urine back into the blood. When the cadmium concentration in these cells exceeds a certain threshold, their function is impaired. Calcium and phosphorus, which should be returned to the blood, are lost in the urine. Bones lose their mineral base, become porous, deform, and fracture. underloads that healthy bone would withstand without a problem. In 1968, Iday disease was officially recognized as a disease caused by industrial pollution. This was the first such case in Japanese history. Before this, no disease had been officially classified as industrially caused. In 1971, the court found Mitsi Kazan guilty and ordered compensation to the victims and their families. By that time, there were over 200 confirmed victims. These are documented cases. How many deaths remained unrecorded is unknown. And here's a point that is often omitted when this story is told as a disaster. Iday disease became one of the 4 officially recognized great pollution diseases of post-war Japan. Others include Minomata disease, caused by mercury contamination of Chiso's Minomata Bay, Nagata-Minomata disease, caused by a similar source in another region, and Yokkaichi asthma, caused by emissions from a petrochemical complex. All 4 cases unfolded around the same time. All 4 reached court decisions in the late 1960s and early 1970s. These 4 disasters were direct political impetus for the adoption of Japan's first law on basic measures to combat environmental pollution in 1967 as Special Environmental Protection. This regime was created in 1971 Japanese environmental legislation of the 1970s with its strict standards for industrial discharges influenced the legislation of other countries. The disaster created law. Now let's discuss the mechanism of poisoning in more detail, because this concerns not only the Jinsu River and not only the 1950s. Cadmium is a chemical imposter. Its divalent cadmium ion, that is, a cadmium atom that has lost 2 electrons, is close enough in size to zinc and calcium ions that it is sometimes not recognized by cell membrane transport proteins and allowed through instead of these metals. Cadmium penetrates where it is not invited. It replaces the necessary ions, disrupting the function of enzymes that rely on zinc or calcium. In the kidneys, cadmium binds to a protein called metallothionein. This is a small protein rich in cysteine that the body synthesizes in response to the ingestion of heavy metals, zinc, copper, cadmium, and mercury. Metallothionein retains metal ions, preventing them from interacting freely with other proteins and DNA. This is a protective mechanism, but in the case of cadmium, it acts as a double-edged edged. Metallothionein retains cadmium in the cells of the renal tubules, where it accumulates. The half-life of cadmium in the body is 10 to 30 years. This is not a typo, and I didn't make a mistake with the units. If you regularly receive small doses of cadmium, and you do receive them, I'll tell you where they come from in the next part. The body accumulates it throughout your life. When the concentration in proximal tubule cells exceeds a certain threshold, estimates vary, but 100 to 200 micrograms of cadmium per gram of kidney tissue is typically used. Damage begins. The tubules begin to leak calcium, phosphorus, glucose, and amino acids. All of this is excreted in the urine instead of returning to the blood. In the monographs of the International Agency for Research on Cancer, cadmium is included in Group 1 carcinogenicity. It is a proven human carcinogen. A link with lung cancer from inhalation exposure is considered proven. This link is established based on epidemiological studies among workers in nickel-cadmium and cadmium battery production. There is evidence indicating a link with kidney and prostate cancer, although the evidence base for these sites is somewhat weaker. Why is cadmium considered a carcinogen? Simply put, it interferes with cells' ability to repair their own DNA. The DNA in our cells constantly undergoes minor damage. This is a normal process. Typically, cells have a repair system. Special proteins detect and correct such defects. But cadmium can disrupt this system. The damage remains. The cell continues to divide, now with errors in its DNA. Over time, these errors increase, and the risk of a normal cell becoming cancerous increases. And here's the bad news. There's no simple medication that will remove cadmium from the body. For poisoning with certain heavy metals, doctors sometimes use special scavengers. These bind the metal and help eliminate it in the urine. But cadmium is more complicated. It sits in the kidneys for years, literally becoming entrenched in the tissue, and trying to remove it suddenly can make matters worse. Cadmium begins to move throughout the body, further damaging the renal tubules. Therefore, in chronic cadmium poisoning, medicine primarily addresses the consequences rather than the metal itself. It replaces lost calcium, supports kidney function, and monitors the patient's condition. Why? If you're thinking, well, that's history, that's Japan's 1950s, that has nothing to do with me, wait until the next part. Then I'll tell you where exactly your body is getting cadmium from right now. The source will definitely surprise you. In 1981, physicist Alexei Yakimov was working at the State Optical Institute in Leningrad with samples of colored glass. The institute dealt with applied optics, lenses, filters, and specialty glass for military and scientific purposes. It was a routine, well-funded Soviet scientific organization. The glass Yakimov was working with contained cadmium sulfide nanocrystals, tiny particles embedded in the glass melt. Colored glass with cadmium compounds was already being made by medieval craftsmen. Yellow and orange stained glass windows in old European cathedrals, in Chartres, Cologne, and Canterbury often owe their color to the cadmium pigment fused into the glass. The technology is ancient and well known. It might seem like nothing new, but Yakimov noticed something no one had noticed before. Glasses with the same chemical composition, cadmium, sulfide, all identical, the same chemical formula, CdAds, produce different colors. One sample was blue, another green, other orange. The chemistry was the same. The melting conditions were roughly the same, but the color was different. According to everything physics knew about the substance, this couldn't be true. The optical properties of a substance are determined by its chemical composition and crystal structure, not by the size of the piece, nor by how finely ground the substance is. Gold is yellow in ingots and powder. Copper is reddish in any form. This seemed obvious in a self-evident foundation of materials science. Yakimov began systematically measuring the crystal sizes in different samples using small-angle X-ray scattering, and discovered a clear pattern. Samples with larger crystals, say 6 to 8 nanometers, produced a uniform color. Samples with small crystals, 2, 3, were different. The color was determined not by chemistry, but by particle size. The explanation lies in quantum mechanics. When a crystal is compressed to a size less than 10 nanometers, something fundamental happens. In a bulk crystal, electrons can occupy a quasi-continuous range of energies, so-called bands. In an nanocrystal, electrons are squeezed into an extremely limited space, and quantum mechanics imposes strict conditions on this constraint. The allowed energy levels become discrete like cotton wool, and the distance between them begins to depend on the crystal size. The smaller the crystal, the wider the energy levels are. When an electron absorbs a photon and jumps to an excited level and then falls back, it emits a photon. The energy of this photon is equal to the distance between the levels. In a small crystal, levels are far apart. The photon is at the high energy, blue end of the spectrum. In a large crystal, the photon is closer to the low energy, red end of the spectrum. Thus, simply by varying the crystal size with the same chemical composition, one can obtain any color in the visible spectrum. This is called size quantization. Yakimov observed a fundamentally new physical effect. He published his results in the Soviet journal Letters to the Journal of Experimental and Theoretical Physics in 1981. The publication was published in a Soviet journal which was translated into English but was not systematically followed by Western researchers in this field. In the West, the work went virtually unnoticed. In 1983-84, chemist Louis Bruce, independently of Yakimov, observed the same effect at Palepi Laboratories in Murray Hill, New Jersey, but in colloidal solutions, rather than glass isolytic X. He synthesized cadmium sulfide nanocrystals in a liquid medium and discovered that their optical properties depend on their size. He published his findings in the Journal of Chemical Physics. The scientific community in the West gained access to the results and began to respond. 2 scientists, 2 continents, a Cold War between them. One discovery 2 years apart. Bruce later, when Yakimov's classified work became publicly acknowledged his priority. Later, Mungi Bawendi of MIT, he joined the field method. In the early 1990s, his group solved a key technological problem: how to synthesize nanocrystals with a very narrow size distribution. Previously, any synthesis resulted in a mixture of crystals of different sizes, some slightly larger, others slightly smaller. Each glowed at a different wavelength. As a result, the spectral peak was broad and diffuse. This made the quantum dots imprecise. The color was approximate, not specified. Bawendi developed a method of high-temperature colloidal synthesis with rapid injection of precursors into a hot solvent. With the right parameters, temperature, concentration, and cooling rate, the crystals nucleated and grew almost simultaneously and reached virtually the same size. Narrow distribution, a clear, narrow spectral peak, and predictable, reproducible color. After this, quantum dots transformed from a laboratory phenomenon into a viable technology. In 2023, the Nobel Prize in Chemistry was awarded to three scientists, Mungi Bawendi, Louis Broussais, and Alexei Yakimov, for the discovery and development of quantum dots. The prize money, 11 million Swedish kronor, was divided equally between them. Yakimov was 78 years old and worked for a research company in New York. It took 42 years from his first publication to the prize. Soviet secrecy delayed recognition of his priority for years. The Nobel Committee eventually figured it out. I think of it this way. You people who were physically unable to correspond, who lived in countries officially opposed to each other on all fronts, military, political, economic, came to the same discovery within 2 years of each other. Within 2 years of each other. Neither borders nor secrecy hindered the discoveries. When the tools were ripe and the question was correctly posed, the answer was found on both sides almost simultaneously. This, I believe, says something important about the nature of scientific knowledge. The first commercial televisions with quantum dots appeared around 2013-14. Several major manufacturers released models under various marketing names, QLED, Quantum Dot, and other variations. In the early versions, the nanocrystals were made of cadmium selenide, CDS. Manufacturers didn't particularly publicize this. The word cadmium, with its toxicological reputation, doesn't help sales. But in the sealed television case, the nanocrystals are locked in a polymer matrix and physically isolated from the user. They won't escape during normal operation. This has been confirmed by independent studies, including those commissioned by the European Commission. After the topic of quantum dot composition became public, major manufacturers began switching to cadmium-free alternatives, primarily those based on indium phosphide and NP. These dots operate on the same principle, but the synthesis is more complex and the size distribution is harder to control. In some parameters, primarily spectral peak narrowness and quantum yield, they are still somewhat inferior to their cadmium counterparts. Work to improve them is actively ongoing. In medical and biological research, cadmium and quantum dots remain the working standard, precisely because they are the most studied and reproducible in synthesis. Cadmium selenide nanocrystals, CDS, are typically coated with a zinc sulfide shell. This is the so-called core shell structure. The ZNS shell performs two functions. It stabilizes the core surface, eliminating defects that would quench fluorescence, and physically isolates the cadmium-containing core from the environment, reducing its toxicity. Biological molecules are then attached to the shell surface, antibodies, peptides, nucleic acid fragments, and legends for specific receptors. The result is a biomarker, a particle that specifically binds to a specific molecular target in a cell or tissue and glows when irradiated with a laser. Its fundamental advantage over organic fluorescent dyes is photostability. Organic dyes like fluorescein or rhodamin fade under laser radiation within minutes. The molecule absorbs a photon, becomes excited, emits a photon, but gradually degrades chemically. A quantum dot, when irradiated with the same laser, glows stably for hours. This is critical for long-term monitoring of dynamic processes. A team from Massachusetts General Hospital used cadmium-containing quantum dots to label and track tumor cells in living mice in real time. The work was published in the journal Nature Biotechnology in 2004. This was one of the first examples of quantum dots being used in living biological systems, not in a cell culture dish, but in a living organism. Since then, thousands of similar studies have been published. Now, about where cadmium is found in your life right now. I promised it in the last part. I'm keeping it. The main source of cadmium intake for the average European citizen isn't old nickel, cadmium batteries, or a factory. In an industrial zone, it's food. Specifically, wheat bread, potatoes, leafy vegetables, carrots, and sunflower oil. The chain works like this. Phosphorus fertilizers are produced from phosphate rocks, sedimentary rocks. Phosphorites naturally contain cadmium. Depending on the deposit, it ranges from single to tens of milligrams of cadmium per kilogram of ore. Our Moroccan phosphate rocks, which account for a significant share of the global market, contain an average of 20 to 30 milligrams per kilogram of cadmium. During the standard production of superphosphate or double superphosphate, a significant amount of cadmium is released into the finished fertilizer. The fertilizer is applied to the soil for decades. Cadmium accumulates in the topsoil. It leaches relatively little into deep soil layers because it is firmly sorbed onto organic matter particles and clay minerals and clay. Cereals and root crops absorb cadmium from the soil through their roots. Wheat accumulates it primarily in its grain, sunflower in its seeds, and potatoes in their tubers. In 2009, the European Food Safety Authority published a detailed assessment of a dietary exposure to cadmium in the European population. The conclusion was unsettling. A significant portion of the European population, particularly those with high consumption of cereals, potatoes, and leafy vegetables, that is, people with a traditional European diet, have weekly dietary cadmium intakes close to or exceeding the tolerable weekly intake. These are not risk groups, but ordinary people with a typical diet. In response, the European Commission gradually tightened maximum permissible levels of cadmium in food. The 2021 regulation lowered standards for cereals, spinach, celery, sunflower seeds, and a number of other products. At the same time, work is underway at the European Union level to reduce the cadmium content in phosphate fertilizers. The 2019 regulation set the maximum permissible cadmium content in phosphate fertilizers at 60 milligrams per kilogram of phosphorus, with a planned reduction to 40 milligrams in a few years. The second significant source is tobacco. The tobacco plant Nicotiana tabacum has a high capacity to accumulate cadmium from the soil. When smoked, cadmium passes into smoke and is absorbed through the alveoli of the lungs. The bioavailability of cadmium from inhalation is significantly higher than from ingestion. About 38% of cadmium is absorbed from food and about 50% from smoke through the lungs. According to biomonitoring studies in Germany, Belgium, France, and several other countries, cadmium levels in the urine and kidney tissue of long-term smokers are 2 to 3 times higher than in non-smokers with a similar diet. And separately, if you have old non-cadmium batteries or batteries that have reached the end of their useful life, please do not throw them in the regular trash. Not because it sounds right in a video about chemistry, but because cadmium from batteries stored in municipal solid waste landfills eventually migrates into the leachate and soil around the landfill. This is a measured and documented process. Most large electronics stores and recycling centers have battery containers. It takes 30 seconds. In 1927, at a meeting of the International Conference on Weights and Measures, a decision was made that almost no one remembers today, although it directly affected every person on the planet for the next 33 years. Every builder, every engineer, every scientist, every doctor with a tape measure. Until that point, the official standard of the meter was a physical platinum iridium alloy. It was stored at the International Bureau of Weights and Measures in Sèvres, near Paris, in an underground vault with stable temperature and humidity. Copies were distributed to member states of the meter convention. Every few years, the copies were brought to Sèvres and compared with the original, checking for deviations. The physical standard has a fundamental flaw. but is difficult to fix. It exists in a single copy. It cannot be reproduced with absolute precision. Every copy is slightly different. It can theoretically deform over time, even under ideal storage conditions. Platinum and an ordinary alloy were chosen precisely for their stability, and it is indeed very stable, but not perfect. And most importantly, it cannot be independently reproduced in another laboratory. You have to go to SEV. The atom solves this problem in a fundamental way. Atom cadmium in Tokyo and atom cadmium in Warsaw are absolutely identical. Not approximately, but within the limits of quantum mechanical accuracy, which is many orders of magnitude better than any physical manufacturing. The same goes for the spectral line of cadmium. If a specific line in the spectrum is chosen as the length standard, and any laboratory in the world equipped with spectroscopic equipment can reproduce it independently without traveling north or comparing it to the original. The red spectral line of cadmium with a wavelength of 643.847 nanometers became the international optical length standard. Any laboratory in the world could reproduce it independently. The cadmium atom is identical everywhere. This decision was preceded by extensive work, and here we must mention Albert Michelson. This is the same Michelson who, in 1887, together with Edward Morley, performed the famous interferometer experiment demonstrating that the speed of light is independent of the Earth's motion through the assumed ether. This result became one of the experimental foundations of the special theory of relativity. In 1907, Michelson received the Nobel Prize in physics, the first American to receive this award. In his precision interferometric measurements, Michelson made extensive use of the red spectral line of cadmium. An interferometer is an instrument that compares the path lengths of two beams of light with an accuracy of a fraction of a wavelength. Michelson measured the length of the physical standard meter in units of the wavelength of cadmium light, thus directly linking the physical pond with the atomic standard. His experiments convinced the scientific community that a spectral standard is more reproducible and reliable than a metal rod. This conviction formed the basis for the 1927 decision. The cadmium optical standard remained in effect for 33 years. In 1960, it was replaced by the spectral line of krypton 86, which proved even more monochromatic and distinct. In 1983, the meter was redefined using the speed of light. 1 meter is the distance light travels in a vacuum in 1258,490,458 just a second. This definition remains valid to this day. For 33 years, the cadmium spectral line served as an international, reproducible optical standard for the independent implementation of the meter. An atom of the metal found during a routine test of pharmaceutical powder held the neutron system of units. Now let's talk about why cadmium ended up in solar panels. And this is truly unexpected. One of the most successful materials for solar energy is a compound of cadmium and tellurite. Scientifically, it's called cadmium tellurite. The secret is that it captures sunlight very well. For a solar panel to generate electricity, a very thin layer of this substance is needed, literally a few micrometers thick. By comparison, classic silicon panels require a layer hundreds of times thicker. This means that fewer materials are required to produce such panels, which means they can be cheaper to manufacture. This is precisely the foundation upon which the American company First Solar, one of the world's largest manufacturers of thin-film solar panels, has built its business. Their mass-produced panels convert approximately 18 to 19% of the sunlight that hits them into electricity. This isn't a world record, but it's a very good figure for mass production. According to the latest data, First Solar has already installed solar panels worldwide with a total capacity of tens of gigawatts. This is a huge figure. The main question on everyone's mind is it safe? Under normal conditions, such panels are completely safe. The material inside is sealed. It doesn't spill, evaporate, or fly away with rain. Even in the event of a fire, studies show that cadmium emissions outside the burning structure typically remain at very low levels, far below what could pose a real danger to people. The main problem arises not during panel operation, But when it fails, the service life of such panels is approximately 30 years. When they begin to retire en masse, the question will arise of what to do with the tons of used modules. First Solar already offers a program for returning old panels and recycling materials, but this is a voluntary initiative. Legislation is already in place in Europe requiring manufacturers to accept returned solar panels and dispose of them properly. The rest of the world is gradually moving in the same direction. Of course, scientists are not sitting idle. Alternative cadmium-free solar panels are already being developed. For example, perovskites. These panels have demonstrated even higher efficiency in laboratories, but they have their own problem. They often contain lead, and it is still unclear how durable they will be in real life, exposed to rain, heat, and frost. Therefore, cadmium telluride remains an important and viable technology. Incidentally, cadmium not only helps generate energy, but also protects health. Its compound is used in modern medical detectors for X-ray examinations and tomography. Such detectors allow doctors to obtain clear images with a lower radiation dose to the patient. If you've ever had a PTS scan or more complex X-ray diagnostics, there's a chance that CDMI indirectly helped your treatment. TZT detectors are also used in nuclear material inspection systems at customs posts in seaports, as well as during inspections of nuclear facilities by international organizations. High energy resolution allows not only to detect the presence of radioactive material, but also to identify the isotope based on characteristic lines in the gamma spectrum. Aircraft coatings. Cadmium plating is the electrolytic deposition of a thin layer of cadmium on steel and titanium parts. It provides one of the best anti-corrosion coatings for use in marine and aviation environments. Bolts, chassis fasteners, and structural components of naval aircraft are often coated with cadmium. In terms of adhesion to high-strength steels, resistance to galvanic corrosion when paired with aluminum, and lubricating properties during assembly of threaded connections, cadmium coating has no complete analog in a number of applications. Zinc, nickel, and zinc cobalt coatings are being actively developed as replacements. They are already used in many civil aircraft components, but full adoption is slow, especially in areas where reliability requirements are most stringent. Finally, there's an application I'd rarely heard about in popular materials about cadmium until I started preparing this issue. Paleoclimatology. In the oceans, cadmium behaves biogeochemically similar to phosphorus. Phosphorus is a key nutrient for marine phytoplankton. In surface waters, where active photosynthesis occurs, plankton consume phosphorus and, along with it, take up cadmium. The concentration of both elements in surface waters decreases. In deep waters, where dead organisms sink and where organic matter decomposes, phosphorus and cadmium are released. Their concentrations are higher there. This behavior is recorded in marine sediments. The shells of planktonic organisms, primarily foraminifera, contain cadmium captured from the water during the organism's life. The cadmium to calcium ratio in the shells reflects the cadmium concentration in the water at the time of their formation. The isotopic composition of cadmium in sedimentary layers of different ages allows us to reconstruct the productivity history of the surface ocean. How intensive was photosynthesis during different climatic periods? How did water circulation change? Using this data, scientists reconstruct the Earth's climatic history over hundreds of thousands of years, through glacial maxima and interglacial periods, and through changing currents. Cadmium stores information about the state of the oceans in the deep past. The pharmacy inspector from Hanover, who, in 1817, did not decipher the strange yellow sediment, was unaware of this. And now, a final discussion about where we are now. The Itatai and eye disease lasted for several decades before the culprit was officially identified. Nickel-cadmium batteries were discarded in regular trash around the world until separate collection laws were enacted. Cadmium stabilizers for PVC were used in the production of pipes and window profiles until they were banned in the European Union. Cadmium in phosphate fertilizers accumulated in soils until standards for its content were established. In all these cases, knowledge existed before action. Cadmium toxicity was documented in scientific papers long before the court decisions in the Mitsui Kazan case. Data on cadmium accumulation in soil from fertilizers were published long before regulatory standards were adopted. Research on cadmium levels in food existed long before the stricter permissible levels. This is not a unique story for cadmium. It is a general pattern in how society reacts to information about toxic substances. Knowledge appears in the scientific literature, then slowly penetrates regulatory bodies, and then discussions begin, including those interested in continuing production without changes. Then something happens that makes further delay politically impossible: a lawsuit, a public disaster, or the accumulation of epidemiological evidence. Then comes regulation. We are now at another stage of this road with regard to cadmium. The knowledge is quite comprehensive. The mechanisms of toxicity have been studied in detail. The main routes of cadmium intake have been measured and documented. Monitoring tools, population biomonitoring, soil monitoring, and food analysis exist and are used in Europe, Japan, and North America. Replacement technologies are actively being developed in batteries, pigments, PVC stabilizers, detectors, and solar panels. Legislation exists and is being updated. JASA standards for cadmium in fertilizers were tightened in 2019. Food standards in 2021 paneled. Disposal requirements in 2023 ado. This is a different situation than the banks of the Zinsu River in 1950. This is no reason to relax. But it is a different situation. Cadmium is not going anywhere. As long as zinc is mined, cadmium exists, an inevitable geochemical companion. As long as nuclear reactors with control rods operate, cadmium exists. As long as solar fields are built using cadmium telluranium, cadmium exists. As long as cancer is diagnosed using CZT detectors, cadmium exists. As long as researchers observe living cells using quantum dots, cadmium exists. As long as paintings by Van Gogh and Manet with cadmium pigments hang in museums say cadmium exists, slowly changing within the canvases. One element with 48 protons, discovered by accident while testing pharmaceutical powder more than 200 years ago. It found a place in the paints of impressionists, stopped and restarted the first controlled nuclear reaction in history, killed people through a polluted river, and helps reduce radiation doses during cancer diagnostics. It serves as the basis of the global MEP system for 33 years, received the Nobel Prize for its first publication, Preserves History of Ancient Ocean. Preserves the history of ancient oceans in its isotopes, and is glowing on your TV right now. Friends, write in the comments which element you want next. Based on your comments, it became clear that we should continue the line of metals in the periodic table to the end, and only then move on to gases. We read all the comments. It is they that we rely on to guide the channel's development. Thank you for your feedback, and see you on the Fool's Gold channel. On the channel where chemistry and physics begin with formulas but always lead to people, technology, and consequences. See you there.